Okay, folks. In the previous kind of long example, I used the technique of logarithmic differentiation to sort of use log properties, simplify, you could argue, or break up a function, and then use implicit differentiation on both sides to find the derivative. So kind of a fun technique, kind of a cool technique, kind of messy though. So at the end of that example, I did it a different way, right? So we didn't need to use that method all along. Here we're going to do a function where we have to use that method. And this is kind of an interesting looking function. Let's try x to the x, right? X raised to the x. What is that? What type of function is that? Well, it's not a power function, right? Because it's sort of like an exponential function because I've got a variable as my exponent. But it's also kind of like a power function because I've got a variable here. So we can't use either rule though. We can't use a power function. The base is varying, so we can't just use an exponential. So we're kind of stumped. We don't really have a technique to evaluate that yet. So let's go ahead and call it y. That's how we're going to set up using this logarithmic differentiation. And let's just go ahead and apply natural log to both sides. That's what we did in the previous example. Seemed to work out, seemed legitimate, seemed fair, in other words, that we're allowed to do that. So let's do that. So I'm going to say natural log of y is equal to natural log of x to the x. All right, great. What can I do here? I've got natural log, I've got this exponent, right? So we can bring the power down. So here I've got x times natural log of x. So bring this x down using one of our log properties, and we've got that. Okay, let's apply d dx to both sides. So I've got d dx of natural log of y is equal to d dx of x times natural log of x. Okay, here we've got a function of y that I'm taking the derivative with respect to x. So it's a little mini chain rule application. I worked this out in the previous video. What I'm going to do for the chain rule is d dy natural log of y times dy dx. Right? In other words, take the derivative with respect to y of natural log of y. That's going to give me 1 over y. And then we just multiply that by dy dx, or y prime. Okay? So just a little chain rule application of natural log. That's pretty common, in fact. If you take the derivative with respect to x of natural log of u, it's always going to work out like this. 1 over u times u prime, and a lot of times they'll just put u prime up top then. U prime over u. So that's a little cool shortcut for the chain rule application of natural log. So that's what we get over here, right? That's always going to happen when we use this technique. And on the right-hand side, I've got a product rule that I've got to do, though, because I'm taking the derivative with respect to x. I have functions of x, so no chain rule that I've got to worry about, but I've got a product, so I've got the product rule. So let's say the first times the derivative of the second. So I'm going to do the first function, x, times the derivative of the second. I'll write it out first and then replace them. Plus the derivative of the first, d dx of x plus, times the original second, natural log of x. Okay, well, x times the derivative of natural log of x is 1 over x. So we end up with x times 1 over x. Plus the derivative of x with respect to itself is a 1. So we get plus 1 times natural log of x. So plus natural log of x. And x over x is 1. So we've got that. So there we go. So 1 plus natural log of x. Let me tighten that up a little bit. And just like we did in the previous video, we want to solve for y prime. So how do we do that? We multiply now both sides by y. So multiply this side by y, multiply that side by y. What is y? We'll substitute back. Y was x to the x. All right, so what are we going to end up with? Y prime is 1 plus natural log of x times x raised to the x, times that original thing. Okay. There we go. Kind of cool. There's no other technique really that we have to figure out what that derivative is. All right, so there we go. A little bit shorter example, a little bit cooler example in a sense because we've got to use this technique here. But there we go. You can use this same technique when you've got other functions of x as an exponent. So if you see something like y equals x times sine of x, how would we do that? All right, maybe I'll do one more video, run through one of those, and put it to bed.